In this video I will talk about B, the non-parametric estimation methods for expected shortfall. Alright, I will talk about 5 different methods. The first method is known as the historical method. Right, this is not the same as the historical method that I talked about earlier under the topic non-parametric estimation of var, right? This is slightly different. So suppose these are the losses, right? The first thing you must do is to order the data, order the losses as follows. So this is the smallest, this will be the second smallest loss, and this will be the largest loss. Alright? Okay, so this is the smallest of the losses. And this is the largest of the losses. Right? Then the estimator for expected shortfall is given by the following formula: 1 divided by NP in brackets. I will explain what that is. Then sum I from 1 to NP of this. Right? What this means is the integer part of n times p. So you might have seen this before. This means the largest integer less than or equal to x, right? So for example, if you have, say, 6.1, then the integer part is 6. If you have, say, 5.9, the integer part is 5. And if you have, say, 0.5, the integer part is 0. Right? So that's how it works. So it's the largest integer less than or equal to x. Right? So these are some examples. Right? All right. So that's okay. Now let me do one example on on this formula before I go to the next method. Right? So this is example 1. Okay. So suppose the losses are as follows. 9 minus 10, 2, 0, 5 minus 5. So the first thing you need to do is to order them. So the smallest is minus 10. This is the next smallest, 0, 2, 5, 9. So this is your x1 in brackets. This is your x2 in brackets, 3 in brackets, 4, 5, and this is 6. Right? Now suppose you want to find the estimator for expected shortfall at 0.2. So this, according to the formula, is n times 2, n times 0.2 is, n is 6. Okay, so 6 times 0.2 is 1.2, right? So it's the integer part of 1.2. Then I from 1 to the integer part of 1.2 of this. Now the integer part of 1.2 is 1, right? So this is simply 1 divided by 1. So I from 1 to 1 of this, which is clearly equal to minus 10. All right? Now suppose you want to find the expected shortfall at 0.9. Right? In this case, it will be 1 divided by n times p, which is 0.9 times 6. So is 5.4, the integer part of 5.4. Then I from 1 to the integer part of 5.4 of this. Right? The integer part of 5.4 is 5, so this will be 1 over 5 times the sum I from 1 to 5 of this. Right? Now if you do this, if you sum the first 5 smallest losses, right, and then divide them by 5, you will get this. Right? Right, so this will become minus 8 divided by 5. Okay, so this is just one example on the historical method for estimating ES. Right, the next method I'm going to talk about is known as the Bootstrap Method. So it has parallel to the Bootstrap method I talked about for nonparametric estimation of VAR. All right. So once again, suppose that these are the losses, and compute the empirical CDF of the data as follows. So f hat is denoted by I from 1 to n of the indicator function okay, where I denotes the indicator function. And, in the video on nonparametric estimation of VAR, I drew a picture of this, so you may recall how this looks like with respect to x. Now the procedure okay, is as follows. So the first step is to simulate b is an integer, alright, simulate b independent samples, random samples, each of size n from f hat. As I said before, there are routines in the R software for doing this. Second step is to use the historical method, which I talked about just a few minutes ago, to estimate ES for each of the B samples. And this results in the following estimators. So for the first random sample, let this denote the estimator, right? For the second random sample, let this denote the estimator, right? And so on. You have B random sample, so let this denote the estimator for the Bth random sample, right? And the final step is to estimate the overall expected shortfall estimator as the following. So you take the mean of these values, okay, or you take them as the median Alright, so this is very similar to the Bootstrap method that I talked about under the heading Nonparametric estimation of var. Okay. Alright, so this is the second method. The third method for estimating ES is as follows. This is the Jackknife method. Again, we talked about this method under the heading Nonparametric estimation of var. So suppose one more time that suppose these are the losses. The procedure is as follows. Right. The first step is to use the historical method . for the data where you drop the first observation. So the data goes from x2, x3 up to xn, resulting in the estimator, say, let me denote it by this. Okay. The second step is to use the historical method to estimate ES for the data, for the following data. So you see here that I'm dropping the second observation, okay, resulting in this estimator ES, okay, and you keep doing that until the last step where you use the historical method to estimate ES for the following data. So the data are x1, x2 up to xn minus 1. So I'm dropping the last observation, resulting in the following estimator. Alright, so you have n estimators, right, and obtained by dropping one data at a time, right? So the final step is to estimate the overall estimator for ES as the mean or the median. So it can either be the mean okay, or the median. Okay, so this completes the Jackknife method. And the fourth method I'm going to talk about is known as the kernel method. So this has parallel to the kernel method I talked about under the heading non-parametric estimation of var. Okay, so this is number 4. Kernel method. Now suppose once again that x1 to xn are the losses, right, then the kernel estimator of ES is given by the following formula, right? okay, where Q hat is the sum 1 to n of the integral from I minus 1 divided by n to I divided by n of k h. I will define this in a minute. Write this in brackets multiplied by the ith smallest data, right? Okay, and the function a subscript u is defined as a at u divided by h. All right, and the function a is defined as the integral from minus infinity to x of ku du, and the function capital K subscript h is defined as 1 over h times capital K at u by h, and the function k is the kernel PDF, the kernel PDF, and it's usually, as I mentioned before, it's usually it is chosen as the PDF of the standard normal. So in other words, k at x is equal to 1 over this times this. I'm sure all of you know this is the PDF of the standard normal. And h is the bandwidth, so it controls the smoothness of the estimator. So if h, for larger values of h, it will be the estimator will be more smooth, and for smaller values it will be less smooth. And finally, these are the losses arranged in increasing order. Okay. So are the losses arranged in increasing order. All right, so that's the fourth method. It looks kind of complicated, but there are, you should know the R software. There are functions in the R software that can actually compute this directly for you, right? So it's not really difficult to compute this. Okay. All right. The fifth and the final method for estimating ES non-parametrically is the following. So number 5. This method is known as the Richardson's method. You may wonder who the Richardson is. Actually, Richardson was a professor at the University of Manchester. His photo can be found at the ground floor ATB Alan Turing building, right? So next time you go to Alan Turing building, you may be able to see the picture of Professor Richardson. So this method is named after him, right? So once again, suppose these are the losses, right? And all right, the procedure procedure is as follows. All right, step number 1 is to compute f hat, which is the empirical CDF of the losses. Okay, right. And step 2 simulate a random sample of size n. Here capital N need not be the same as little n. They are not equal, right? They may not be equal from f hat. And as I said before, there are methods in R for simulating from the empirical CDF. Step 3 is to use the historical method to estimate ES for the data that you simulated in step 2, right? Okay, so and step 4 is to repeat step 2 and step 3 1,000 times. Okay, so you're going to repeat over these 2 steps 1,000 times. And step 5 is to compute the following. Right here, this thing here denotes the historical estimator for the ith iteration, because you are repeating these 2 steps 1,000 times. So this denotes, so let me write it down, where Alright, so it denotes the historical estimate of expected shortfall at the ith iteration. Right, so that's step 5. Now step 6 is as follows. Set Sj equal to m subscript n subscript j for j from 1 to up to k plus 1. Alright, for some k and n1, n2 up to n k plus 1. Okay. Alright, so for example, you could choose k to be 1, n1 to be 100, and n2 to be 1000. Right. So for example, you could choose k to be 1 and n1 to be say 100 and n2 to be say 1000. Okay, and the final step is to compute the expected shortfall as follows. Give me some time because it's going to take a while to write this down. All right. Alright. So it's going to be the determinant of this matrix, right, divided by the determinant of another matrix. This is 1, 1, 1, half, okay. Okay. So this is so it's estimated as a ratio of the determinants of these two matrices, right? Okay. So that completes the Richardson's method, and it also completes the nonparametric methods for estimating expected shortfall. In the next video, I shall talk about semi-parametric estimation of expected shortfall.